start on time. It's a great pleasure to introduce John Coates here in Cambridge, who's going to talk on more about the Iwasawa theory of elliptic curves. Thank you, Richard.
So I want to begin by talking about this general MH of G conjecture that was talked about yesterday, and leading up to, and for the moment I'm not going to assume at all that the curve has complex multiplication. It will only be when it comes to a couple of applications later that I will do that. So I'm going to assume I have my base field will be a finite extension f of q, and I have an elliptic curve over f. Take the switch. So I have an elliptic curve over f, but in fact, practically everything I say would hold if I worked with any motive, for example, the Tate motive or something like that. I mean, apart from the precise statements of the theorems, but I think it should work for a large class of motives. But let's stick to an elliptic curve. We could equally well take an abelian variety. And I remind you, and now I take P to be a prime number, and again for simplicity, I'm going to assume P is odd. And let me remind you that if I have any algebraic extension L of the base field, then this is the classical Selma group, which in some sense goes back to Fermat, of H1L is the kernel of the H1L EP infinity into the product of all the local H1LWs of all the points on the curve. And then, as usual, I'm going to write X of E over L for the Pontryagin dual of that, and we'll tend to work with the compact Pontryagin dual. And, of course, if L is a Galois extension of F, then the Galois group of L over F acts naturally on these objects, and it's that action which is somehow that the main conjecture and so on is all about. Now, I want to begin by reminding you of the very first conjecture that was made by Mesa long ago in the Iwasawa theory of elliptic curves, because what I'm talking about is very closely related to that. So let me write F cyclotomic for the cyclotomic ZP extension of F, and I'm going to write Galois for the gamma for the Galois group of F cyclotomic over F, and lambda of gamma for the Iwasawa algebra. And now I'm going to assume throughout the lecture that E has good ordinary reduction at all primes of F above P. In fact, with, again, some modifications perhaps in the statements of theorems, you could just suppose this potentially good or potentially multiplicative reduction at all primes above P. What is fundamentally different, and we don't know how to handle at all for the general case, is when there's potential supersingular reduction.
For motives, what would you assume?
Again, well, I'd have to assume that representations are ordinary, the Galois representations, exactly. And then let me remind, so Mesa made this conjecture that X, the dual of Selma, whenever you're in this situation of E over F cyclotomic, is a torsion module over the Iwasawa algebra. It's obviously finitely generated, but it's in no way obvious that it's torsion. So that's Mesa's conjecture, which has been proven in some interesting cases, but I'm not going to discuss that except for one application later. And let me remind you that from the structure theory of torsion lambda gamma modules, we know that Mayes's conjecture is exactly the same as saying that if you take the dual Selma and you divide by its p primary submodule, the submodule of all elements killed by a power of p, then this should be a finitely generated ZP module. That's what it amounts to. So now the question we want to consider is, how do we generalize this to a large class of p-adic Lie extensions of F? And so I'm going to consider now a p-adic Lie extension here, which I'm calling F infinity. And I'm going to assume now that firstly, of course, it's unramified outside a finite set of primes. We always are going to assume that. I want to assume, of course, that its Galois group G is a p-adic Lie group. And the third thing I want to assume, which is basic for us, is that it should contain the cyclotomic ZP extension of F. And a typical example is when you adjoin to F all the coordinates of all the p-power division points on the curve. No, in a moment I'm going to assume, I'm going to rule that out. But for the moment, sure, it can have anything. So now, the naive generalization of Mayes's conjecture to this situation. So now you can look at the dual of Selma over F infinity. And of course, the naive generalization, which was actually conjectured by Michael Harris long, long ago, is that X of E over F infinity is a torsion lambda G module. And torsion, of course, because there might be zero divisors, means every element is annihilated by some non-zero divisor in lambda of G. But the trouble with this, so this is the obvious generalization of Mayes's conjecture, but the trouble is it's not strong enough to make a main conjecture. That's the whole problem, that we don't we don't know how to define a characteristic element for arbitrary torsion lambda G modules once G is a non-abelian group. So in fact, inspired by some work of Venyakov in this Fiver author paper, which he mentioned yesterday,
What does torsion mean? Was there some element which
there is just for every no, not a global element. Just for every element, there is an annihilator which is a non-zero divisor. So in this paper, we realized that if you instead introduce what's called the MH of G, so H, of course, I'm sorry, it's over here. H is the subgroup of G which fixes the cyclotomic ZP extension. So G mod H is isomorphic to gamma. And so the conjecture that we made is that if you divide out the dual of Selma by its p primary subgroup again, then it should always be finitely generated over lambda H. And as Ottmar was explaining yesterday at the beginning of his lecture, this then enables you to make an absolutely precise main conjecture. And of course, the reason why you want to make a precise main conjecture is you want to deduce all the exact formulae, or as much as you can of the exact formulae, like Birch and Swinnerton Dyer and so on, from knowing this main the finite extensions inside your p-adic Lie extension, and for many other reasons. It's the way in number theory of somehow linking the L values to the arithmetic. But now I want to say a little bit about this conjecture, what it really boils down to. So I want to now make the assumption that, which I can always, by enlarging my base field f, if necessary, a little bit by finite extensions, this will be true. I want to assume that G is pro-P and has no elements of order P from now on. So that's the basic assumption. And then, in fact, it's well known that this implies that the Iwasawa algebras, lambda G and lambda H, are local rings. So then you see, once you have a local ring, you have Nakayama's lemma. And so, as a result, you immediately see that that if x of E over F cyclotomic is a finitely generated ZP module, then it's immediate from Nakayama's lemma. Well, of course, sorry, it's immediate. You have to relate x of E over F cyclotomic to the H co-invariance of x of E over F infinity, but it's very easy to see that if x of E over F cyclotomic is a finitely generated ZP module, these H co-invariants differ from it by a finitely generated ZP module, and so you can apply Nakayama's lemma and deduce that the whole module is finitely generated over lambda H. But of course, the whole difficulty in general, so this conjecture is easy to prove if you're lucky enough for the Selma group dual Selma over the cyclotomic ZP extension to be a finitely generated ZP module. But unfortunately, it's not the case, always. It's quite often the case. And I mean, in fact, Maser, this is one of the things he pointed out in his first paper, that that this phenomenon, that the P primary part need not be a finitely generated ZP module. You have this phenomena of positive mu invariant coming in. Now, I should mention that in the parallel case of the Tate motive, this was a celebrated conjecture of Iwasawa's, which is still open, but which has been proven in some cases, and we'll talk about one case in a moment, that in fact the analogous module is always a finitely generated ZP module. This is his mu equals naught conjecture. But for elliptic curves, that is not the case. Already x naught of 11 and p equals 5, you have a positive mu invariant. So I now have to say what this conjecture boils down to essentially, and remind you what the mu invariant is. So what you have to remember now, you see we have two extensions here. We have the p-adic Lie group G and gamma. And we have mu invariants for both G and gamma. But they're defined in the same way. So let's take the classical case of gamma. If you have a finitely generated lambda module, and then I'm going to write tilde now for the notion of pseudo-isomorphism in commutative algebra. That means the localization at every prime ideal of height 1 is 0. Then in fact from the and if I write as usual MP for its p primary part, then the structure theory tells you that that's pseudo-isomorphic to an elementary module of this form, a direct sum of lambda gammas modulo p to the m1's lambda gammas. And then the mu invariant is just the sum of these exponents that you have here. Let me also just mention in passing that the mu invariant is easy to see also is, or p to the mu invariant is the gamma Euler characteristic of MP, which has to be finite, of course. It's automatically finite.
Excuse me, could I ask about that Maser's counterexample? Would you conjecture that even for elliptic curve, there exists a p with mu invariant?
No. It's quite the opposite. In fact, we'll prove later for CM elliptic curves it is 0.
Right, but even in general, what would you say if somebody asks whether there exists a p?
No. I mean, the general feeling, it's a little more complicated over Q, but The only time it can happen is when the p division points are reducible. When you have an isogeny of degree, I think.
Well, I see, yeah.
Could you repeat what your answer was?
I said it only, I guess it's unproven for arbitrary curves, but the conjecture is that over Q, you can only have a positive mu invariant for the prime p, for your elliptic curve, if there is an isogeny of degree p defined over Q. I think over a number field there are counterexamples to that. I've forgotten now, but no, it should only happen exceptionally. But it happens, so that stops you proving theorems. It's the biggest bugbear in some sense in the whole Iwasawa theory of elliptic curves, that you have this positive mu invariant. So now if you have instead a finitely generated lambda G module, then we have a entirely analogous definition. If n is a finitely generated lambda G module, again tilde is O. Of course, pseudo-isomorphism in the non-commutative case requires some explanation, which I'm not going to go into now, but there is a notion. But again, if G was Zp to the D, then in fact it would be just the usual old definition that you find in Bourbaki. But Otmar-Venyukov proved that if you look at the p primary part of this module, again it's pseudo-isomorphic to a lambda direct sum of lambda G's mod principal ideals generated by powers of p. And so again, you define the mu invariant of M to be the sum of these exponents n1 through nh. And in fact, I should also say it's again true there that the p to the mu invariant is the G Euler characteristic of NP. It's always related to Euler characteristics of the p primary submodule. So now I'm not going to make a precise statement here because we'll come to it in our specific case in a moment, but in fact you see quite easily by looking at the comparison of what's happening over F infinity and over F cyclotomic that the MH of G conjecture is very closely related to saying that the G mu invariant of x of E over F infinity should be the same as the gamma mu invariant of x of E over F cyclotomic. There should be this equality of mu invariance. So now what I want to talk about is that and I should have said everything I'm saying now in this work is joint work with Sujata, but I want to talk about a proof that we have found of this MH of G of conjecture in the simplest case when G is Zp squared. So that's what I want to talk about for the rest of the lecture. So here is the precise statement of the theorem. So I assume that the Galois group of my p-adic Lie extension is Zp squared, and now this is that we're assuming that x of E over L cyclotomic, we're assuming Mayes's conjecture for every finite extension L of F contained in F infinity. So in fact, I should have said that earlier, but it's easy to see that the MH of G conjecture, if it's true, that implies, and this has got nothing, this is true for any G, that implies Mayes's conjecture for every finite extension of the base field contained inside the p-adic Lie extension. That's easy to see, and in some sense the hope is, that's what this sort of argument is all about, that you can go back the other way. In other words, if you know Mayes's conjecture for the cyclotomic ZP extension of every element of every finite extension of F contained in F infinity, then the hope is that you can prove the MH of G conjecture. So that's what we believe we've done here in this case, when G is ZP squared. What the argument actually shows is that the G mu invariant of Selmer of E over F infinity is indeed the gamma mu invariant of X of E over F cyclotomic, and that does, it's easy to see, that implies the MH of G conjecture. So this is the theorem I wanted. And it turns out the proof is shockingly elementary, and I don't see any mistake in it. So I want to explain it to you, but first let me say these two remarks, and then I want to discuss some applications before I get down to the proof. The first thing is we actually believe that, although we haven't written everything down, that the proof goes through for ZP to the D, for any D greater than 2, greater than or equal to 2. That there are some additional complications, as we'll see, but we believe we can handle them. And again, we have high hopes, although we've done no work at all except vague thoughts about extending it to the case of non-commutative G. And the arguments are purely algebraic and arithmetic. There's no analytic side at all in the arguments. But now what I want to say is that if we combine that with some work done a long time ago by Gillard and Schneps, in fact it's Schneps's thesis, but also long ago, that we get some particularly interesting consequences for the special case now of elliptic curves with complex multiplication. So the theorem I'm proving got nothing to do with complex multiplication, but now let me assume that I just want to explain these consequences. So the first is that if you have an elliptic curve over Q which admits complex multiplication, and you take a prime at least 5 of good ordinary reduction for E, then in fact the mu invariant of Joule-Selmer over the cyclotomic ZP extension is 0. Now I have to say this had always puzzled me, because somehow Mayes found these beautiful examples like x naught of 11 and so on, but there were no examples for CM curves, and there seemed to be no reason why. Although I realized later when we made the MH of G conjecture that it explained why, and that's what's behind the proof of this. So I now want to discuss that a little. So this is a special case of a more general result that I want to explain now. So I'm going to take K to be an imaginary quadratic field of class number 1, and I want to let OK be the ring of integers of K.
Oh, sorry, in relation to your comment, does this not work for p equals 2 or 3?
Well, I think for p equals, well, it's got to be ordinary, but for p equals 3, I believe that it certainly must with a little bit of trouble. Because they only, of course, with somehow 2 and 3, if you're working with the field of p-power division points on elliptic curve, they're nasty, and they just didn't do it in their papers. But I think p equals 3 should be all right. P equals 2, is a nightmare in Iwasawa theory. So I have no predictions there.
So somehow there is a sense in which the CM case is really different.
Yeah, and it has to be. It has to be, or the MH of G conjecture would fail. So for the next corollary, which in fact implies the one I said, I'm going to allow a slightly more general class of curves rather than just defined over Q. I can allow them to be defined over K.
This quadratic imaginary.
Yeah, this imaginary and I want to assume that the endomorphism ring is the maximal order of K. So what you really need, by the way, to make this kind of proof, perhaps I should say it, is that you could work over a finite extension of K, provided the p-power torsion points on the curve generate an abelian extension of K. You can't work with elliptic curves with complex multiplication in general. You must have that the p-power division points are abelian over K. But the result is that if you take a prime at least ply which splits in K and for which E has good reduction at both primes of K above P, and then you take F infinity to be this K adjoin EP infinity, then in fact the P primary part of the Selma group of E over F infinity is 0. There is no P primary part in this case, and X of E over F infinity is a finitely generated lambda H module where H is, as usual, the Galois group of F infinity over K cyclotomic. So you get the MH of G conjecture for CM elliptic curves of this kind, which of course includes many of the sort of famous historical families of curves. Now, the last thing I want to say is that it also has an easy application to the classical Iwasawa mu equals naught conjecture for the tape motive. So, let me remind you what that conjecture is. So let's take Iwasawa conjecture the following. If you take any finite extension f of q and you let LF be the maximal unramified abelian p extension of f cyclotomic. This was the first module he ever studied. And then he conjectured that this, for the remember it's a cyclotomic ZP extension, that the Galois group of this extension over F cyclotomic is always a finitely generated ZP module. This is his mu equals naught conjecture, that there's no mu invariant there. And so the corollary, by an easy argument from this result, is that if you have a prime, again at least 5 because we're assuming using their work, which splits in K, and you let F be any finite abelian extension of K of degree prime to P. But it's and the condition, by the way, prime to P can probably be removed by redoing their work. Then, in fact, the Iwasawa mu invariant conjecture is true in this case. So these are the first examples where we can actually prove it for abelian extensions of imaginary quadratic fields.
Are these columns of your theorem?
Yes, they're all.
In the theorem you have a ZP square extension. What happened to that?
Yeah. Well, the ZP. Well, I'll explain a little bit about the proof in a moment. The point is that if you look at this extension here, F infinity equals, where are we? K adjoin EP infinity. It is a ZP squared extension of K adjoin EP because there's CM. That's the point. So you're applying it to that extension, in fact. But that you also need this other result, which I now want to say a little bit about.
Is this last corollary independent of Washington's theorem?
Sorry?
This last corollary.
Yeah, it's nothing.
It's independent.
No, I mean, it's based on Sinnott's work. I mean, Gillard and Schneps generalized a beautiful argument of Sinnott's for proving that the Iwasawa mu equals naught in the abelian case. It generalizes to this.
So you're saying only has to be abelian over K.
That's the point, yeah. It's not abelian over Q necessarily. So I just want to mention what's lurking behind this, deriving these corollaries from the theorem. So what you do is you pick, I mean, suppose we have an abelian extension of K, we pick an E over K, we look at, with complex multiplication, we look at the field F adjoin EP infinity, and then there are two key things you see you have to prove to apply the theorem. Firstly, you have to prove this statement that X, for that now, so our tower is F infinity down to F, and we have to prove May's conjecture for every finite extension in there. And now, happily, there is a beautiful non-vanishing theorem of Greenberg. Well, you have to do that, you have to use the main conjecture in the weaker form without the MH of G conjecture that Ottmar talked about, plus this beautiful non-vanishing theorem of Greenberg's. You have to know certain complex L values are not zero when you go up. You have to know at least one is not zero when you look at your elliptic curve over your field F, or any finite extension of F in there, and then you're looking in the cyclotomic ZP extension of, so you're twisting the L function by one of those characters. You have to know that at least one of them is non-zero. And in fact, Greenberg proved this in a very beautiful course of lectures that he gave at Orsay many years ago. And despite my urging him, he's never published the proof properly. So I hope he will, but there's no question the theorem is fine, and and I have detailed notes of the proof and so on. Sorry? The complex L function at S equals 1. No. All you need here is a. So you've got your K, right? You've got this K adjoin, well, F adjoin, well, F, and then we have, so that's an abelian extension of K, and then we have up here F infinity, which is, right, F adjoin EP infinity. And now you take some finite extension in here, and then you look at L cyclotomic, right? And which sits inside there. And what you have to show is that the L, if you take the Grossen character of the curve to be precise, and you take some finite abelian extension, you have to find a character here, right? I mean, you twist, firstly, the L function of the curve over, because this is an abelian extension, will be a product of L psi chi's, where these are characters of finite order of the extension. And then you're going to have to twist that by a character. You have to show that when you twist that by a cyclotomic character, that this is non-zero, provided, well, all you need is that the order, what he proves is that if the order of rho, meaning its order in the group of characters, is sufficiently large, then this is non-zero. So therefore the the p-adic L function of the curve over that extension is not identically 0, and therefore by the main conjecture it's a torsion module. But this is a completely complex argument here. So then you have to invoke, so that's the first thing, and then you have to invoke this work of Gillard and Schnepp's, which in fact they looked at another ZP extension contained in there. They looked at the one in which you see P splits in K, and in which the unique one in which the prime unramified, one of the factors is unramified, and the other one is ramified. And there you could generalize Sinnott's argument to prove that mu equals naught. And so that implies immediately that the mu g of x of e over f infinity is 0. So the mh of g conjecture can only be true if the same is true for the cyclotomic one. And happily it is. Okay, so now in the rest of my lecture, I want to try and explain the proof as much as possible. It's not very difficult in the end. So I go back to my general situation. I have an arbitrary elliptic curve. As I say, there's no, of course, there's no analytic arguments coming in at all. And obviously, so I'm assuming the Galois group of f infinity over f is zp squared. So I can fix a zp extension L infinity of f such that then I can write, I have this nice square here where g is h cross gamma. Okay, and so I have these two zp extensions of f, and their composite is the whole thing, and the intersection of the two is f. And so I'm writing h for the Galois group of f infinity over L infinity, which of course I can identify with the Galois groups all the way down there. If I take any finite extension inside f, inside L infinity of f, again the Galois group, when I take it cyclotomic, will be precisely gamma. Now I just want to make one remark that it's easy to see that if you have Mayes's conjecture all the way up, that it does imply that x of e over f infinity is lambda g torsion. It's not quite obvious, but it's true. So, and since we're assuming that now, we know that our module is lambda g torsion. There's no problem about that. Now I'm going to write y of e over f infinity for the quotient of x of e over f infinity by its p primary submodule. So by definition, y of e over f infinity has p primary submodule, which is 0. And in particular, it has g mu invariant, which is 0. And let's also note that, of course, you can also, which is a useful remark, that you can identify y of e over f infinity with a submodule of x, because it's clearly p to the r x of e f infinity when r is sufficiently large. Oh, I'm sorry. So we'll be interested in the taking H homology. So H, remember, is coming down all the time, or an open subgroup of H will take us down to the cyclotomic ZP extensions that we're interested in. And of course, since H is just isomorphic to ZP in this case, we have that all the higher homology groups for I greater than or equal to 2 of M are obviously 0. So now the first remark I want to make is this lemma that I've written down here. And again, it's a special case of a general phenomena that it turns out, and it's a very happy fact, that if you look at the, and this is true for any p-adic Lie extension, that if you look at the H homology of this x of e over f infinity, then the HI's of H for all I greater than or equal to 1 are finite. Provided it's lambda G torsion, which we believe is always the case. That this just comes out of comparing the two. I mean, I'm not going to give the detailed argument, but it's sort of easy to prove, and it's very nice. This is why there are, in some sense, nice formulae for the lambda H rank and things like that in the arithmetic of elliptic curves. So in our case here, it's even simpler. We only have to worry about the H1, and it turns out to be 0. In fact, you see easily that for all 3 modules, x of e over f infinity, it's p primary submodule, and for the y of e over f infinity, that they're all 0, the H1s of them. So then what you get is this key proposition. Again, I'm not going to give the detailed proof of that, but basically it comes from the remarks that I made about that the mu invariants are the Euler characteristics. And you see you have a nice Hochschild-Sayre spectral sequence. Gamma is relating the G homology to the other, and it comes out very easily. You get this exact formulae here for the relationship between the two mu invariants. So I just want to emphasize that the right, this is the mu G invariant of the module upstairs. This is the mu gamma invariant of the module over the cyclotomic. And then there's this discrepancy term here, which is the mu gamma invariant of the H co-invariance of y of e over f infinity. So y, by definition, has G mu invariant, which is 0. But when you take its H co-invariance, it might well have a positive gamma mu invariant. So in general, you see you get the obvious remark that this G invariant is always less than or equal to that one. But you have to show they're equal, is the whole point. So you can't seem to do anything with this formula at this level, but now the basic idea of the proof is to look what happens to this formula when you... So now I'm going to let Ln be the nth layer of the ZP extension L infinity over F, right? So I'm now going to let Ln will be this sitting inside here, and then Ln cyclotomic will be up here. And the whole idea of the proof is to analyze what happens to this formula when you now replace f by Ln and let n tend to infinity. So of course, if you replace f by Ln, then you've got to look at these various new Galois groups. They're all open in the appropriate, so Gn will be the Galois group of f infinity over Ln, Hn will be the Galois group of f infinity over Ln cyclotomic, and delta n will be this Galois group of Ln over f, which in our case is cyclic of order p to the n. And now we want to analyze what happens when we replace f by Ln and let n go to infinity. So it's obvious what happens to the left-hand side. That's the first remark I want to make. So the left-hand side, remember, is this G mu invariant because Gn is of index p to the n in G, and so the Euler characteristic multiplies by p to the n, and so we get that if I let alpha be the G mu invariant of x of e over f infinity, the Gn mu invariant of x of e over f infinity is p to the n times alpha. It's obvious. However, what is not at all obvious is what happens to these two terms. And that's exactly how it turns out you can prove the equality that you want. So to do that, I need two purely algebraic theorems, which I'm now going to state, and then we'll deduce the appropriate estimates for them. So the first one is the following, that suppose you have, so this has nothing to do with arithmetic anymore, it's just algebra. You have a finitely generated torsion lambda G module, and the crucial thing that I want to assume is that its G mu invariant is 0. So that's exactly true for y. We're going to apply this with m equals y of e over f infinity. By definition, it has mu invariant 0. Probably the next hypothesis is unnecessary, but let me assume it because it's true in our case and it simplifies the proof, that I want to assume that for every n greater than or equal to naught, the Hn coinvariance of m is lambda gamma torsion. Then the conclusion is that the mu gamma invariance of the mh of n's, they may go off to infinity, but who cares? But they're at most a constant times n plus 1. That's the point. And by C1, I mean something which doesn't depend on n. And you see that, now, okay, let's apply that now to our particular case. So we conclude if we if we take that, we have mu gm equals naught, and we're assuming that the x, so that gives us the same thing for y, you see easily. And so, in fact, we get this upper bound. And you see the essential point is that the growth is so totally different to the growth here. It's at most a constant times n, whereas here it's p to the n. Now, I'll say a word about how we prove this. It's just sort of simple algebra well, it's slightly tricky algebra, but dimension theory argument, something like that. I will say a little bit about it later, but now I want to go on to the second algebraic lemma, which is the following, because now we have to say something about the other term, which, let me remind you, is mu gamma of x of e over ln cyclotomic. So what this lemma states is the following, that if you have, so let me write delta any finite p group. It needn't be abelian. And I'm going to be applying it with delta equals my group delta n, but we could take any finite p group. And then we look at, let R be the group ring over lambda of delta with coefficients in lambda gamma. And so the proposition is simply that if you have a finitely generated R module, which is killed by some power of p, and you just impose the very modest hypothesis that the H1 of delta M is finite, that's all you need, then in fact you can compute the gamma invariant of m from knowing the gamma invariant of the delta co-invariance, you just multiply it by the order of delta. So again, this is not very difficult to prove. What's surprising perhaps is you only need to know the finiteness of h1 delta n. It sort of rules out that the sort of obvious contradictions to this don't work. So now we apply that to our, whoops.
For that proposition, do a gamma and delta have to be commuting?
Yeah, of course. Yeah. I'm assuming they're computing when I take the group ring, yeah. So now if you look at, so now you see, now I'm looking at the extension. I'm going to apply this lemma to this finite extension L over F, whose Galois group is delta n. And you take M to be the dual of Selma, x of E over Ln cyclotomic P. And what you see, again, I can't give the argument, but it's a standard conclusion that from this, the fact that both are lambda, you actually need both being lambda gamma torsion to see this, that the H, maybe you can get by with just assuming the bottom one is, but you can actually show rather easily that the H lower 1 delta n of the P primary submodule, so I'm going to take M to be the P primary submodule, of course, because remember by definition that's the same as this. The mu invariant only depends on the P primary submodule. And so, and also it's easy to see that in this case, the mu gamma of M delta n is precisely the mu gamma of x of E over F cyclotomic. So so the conclusion from proposition B is if we let beta be the mu gamma invariant of x of E over F cyclotomic, then we get the one for x of E over L cyclotomic. It just multiplies by p to the n. And so now it's obvious how you complete the proof. You just substitute these two quantities into the formula that we had, and you divide both sides by p to the n. Right, so you get alpha, the left-hand side is alpha times p to the n, and the beta times p to the n, so you divide through, you get a over p to the n there, and then you let n tend to infinity, and of course, because of our estimate up here, this term tends to 0. And that does it. So we must have alpha equals beta. Now, in the last 3 or 4 minutes, I just want to explain to you the completely by the way, I should say that, maybe I should say this, a few words about going back to this. So I want to talk about now the proof of this statement here. Now, I'm going to explain to you how, at least for the main part of it, it's a completely elementary argument, in this case of d equals 2. For higher d, I should say here that you will have to have a power of p to the d minus 2n coming in there, where then, of course, hn will be of index p to the n minus 1 in the thing, and so on. That for higher, if you go to higher d, you have to modify it slightly. Okay, so now I want to try and explain to you how you prove this type of thing, because it's crucial for the whole argument. So I pick topological generators of the subgroups gamma and h, and as usual I let gamma 1 be a variable t1 plus 1 and the other and t2 plus 1, and then I can pick that there. Then the Iwasawa algebra of G, of course, I can identify with the ring of formal power series in these two variables, T1 and T2. And the way in which you, at least the only way we see of proving this kind of theorem, is to invoke the structure theory. So by the structure theory, you see you will have an exact sequence of this kind, the direct sum of R mod principal ideals into M and into D, where D is pseudo-null. And so if you take co-invariance, you immediately get this sequence here that I've written down of the HN co-invariance. And so immediately you get that the gamma mu invariant of this one here is less than or equal to the sum of the gamma mu invariance of the two terms. So so what this means is that you only have to prove this statement for modules of the form R mod FR and pseudo-nulls. That's the reduction. So now I want to explain to you, so that's what I've got here, the argument for R mod FIR, because it's sort of totally elementary, and you can see what's going on behind it. So let's take the case where M is R mod FR, and now the crucial thing, right, and I'm taking HN co-invariance, so I should introduce this. Well, firstly, the crucial thing is, of course, because mu GM is 0, that's equivalent to saying that F does not belong to PR. It's not divisible by P. And you see the HN co-invariants now are simply, because the T2 variable corresponds to H, is simply R modulo F, the ideal generated by F and omega n T2. And then you see easily that the characteristic element of this cyclic module here is precisely this product here, where you take, in the T2 variable, you take the product over all the p power roots of unity and you leave the T1 variable the same. And so we want to estimate the largest, so that what we have, the mu invariant in these such modules will be the largest power of P dividing this power series. So that's what we have to estimate, and it's a completely elementary exercise. So you what you do is you simply look. So we have to determine the order of this Hn, that's the largest power of P dividing all the coefficients. So you simply look at it as a power series like this, and you pick out one of the variables, and of course, because it's not divisible by P, there will be a BK, one of these coefficients, which is not divisible by P. And so that means that one of the coefficients of that power series are not divisible by P. And then what you see immediately is that if you choose some integer, so let's call that beta s, that coefficient, m naught such that phi of P to the m naught is greater than s, then if you have a root of unity, a p power root of unity which is of order bigger than P to the m naught minus 1, the value of this, the order of this at bk of zeta minus 1 is s over phi P to the n. So you just put that in your an upper. So that tells you, if you go back to it, that the order of this factor here is at most s over phi p to the n for all n greater than or equal to m naught. And so you just now look at, you forget about the part of hnt1 which has come from p power roots of unity of order less than p to the n naught. And for the others, you just have this obvious estimate here where you sum, because you have to sum over all the primitive p power roots of unity. There are 5, so you take a p to the r in here, 5p to the r to them, you get s over 5p to the r, you get s times n. And that's it. Now it's slightly, my time is up, it's slightly more, you have to use a different argument perhaps, where you can modify this argument even for the pseudo-nulls, but again you break it up into one in which m is either mp or mp equals naught. It turns out to be obvious in this case for when mp equals naught, because then you see easily that m is a finitely generated ZP module. And then you have to have a separate argument for mp, which I haven't gone into here. So let me end here.
Are there any questions for John? Yeah.
Here, this MHN, is it R? Because you wrote in the previous line F, comma, omega, NT2 is 1.
Sorry, MHN is R divided by F and omega NT2.
That's 1.
Right. Yeah, but I mean, that doesn't, remember, they can be relatively prime, but still.
Didn't MHN just be R not F?
No, M is R mod FR. So MHN, you're now taking the HN covariance, and it really is R mod F omega NT2. I mean, if it was, right, if n was naught, for example, you take R of F mod T2.
When you write that, you don't mean the ideal generated by those two things is 1. You mean they have no common factor that isn't a unit.
Yeah, I mean, it's a unique factorization.
Yes,
So
right.
I
I was
actually
just trying
mean,
to-
that's what you're worried about. No. It's a unique factorization domain. I mean, they have no, in their factorizations, no. That doesn't mean the ideal is 1, of course. No.
Yes.
So once you conclude alpha equals beta, in the inequality something becomes 0. So some mu invariant now, some other mu invariant of y, of the Hn covariance of y is now seen to actually vanish.
Exactly.
Does that have, I sort of lost the third of things slightly, but does that have a kind of meaning or application earlier or later?
Well, no, but it's precisely what would happen. You see, if y of e over f infinity, the MH of G conjecture says it's finitely generated over lambda of h. So therefore, the Hn coinvariance of it, if that conjecture is true, have to be a finitely generated ZP module. And so therefore they have mu invariant 0. So that's all, it's just confirming our desires. And it's always nice to confirm your desires.
Any other questions?
If I could
Yeah.
ask about something a bit earlier on.
Right.
The third corollary to your main theorem, you had this application to the mu equals naught conjecture of Iwasawa. Can you talk a bit about how you get to that from the results you had about elliptic depth?
Well, I mean, basically, I guess you can pass from one to the other if over a field F, if the p power division, the field of p power division points on the curve is pro p over the base field. It's an easy argument with Nakayama's lemma. So it's not quite obvious, but it's an easy argument, yeah.
Right.
looks like everywhere is very essential that the lambda g is commutative, yes, at least lambda h. So what kind of algebra do you expect to have when g is not commutative?
No. The whole, everything that I've said here works basically perfectly well with an arbitrary non-commutative g. It's just that in that formula you'll now have some of the higher h homologies of these y's or the y. I mean, but no, everything I've said basically, the whole principles work perfectly well in the non-commutative case. Except this elementary proof I'm giving you.
I mean, this kind of.
But I think the correct way to prove this type of thing in general is using dimension theory arguments and the Hilbert-Coulomb polynomial and so on. Yeah.
Maybe one more question.
Yeah.
So, to come back to this question about the new environment, what ingredient did you add to what Rubin had to model when it was variable nature?
Well, because Rubin didn't know that the cyclotomic mu invariant was 0.
Use a result of general steps.
No, but that's up the G mu invariant here. So it was unknown that the cyclotomic one was 0. That's the whole problem.
I think maybe we should call a stop now if people have further questions. Talk to